Hello and welcome to this video from libreprogramming.org. This is Shushankar Dayal, and as promised, I'm skipping rather the error handling functions of stdr.h, and I have moved on to Math.h. Now, as you know, C was invented by Dennis Ritchie, and he was a computer scientist, so he gave a lot of math functions with C, and other languages followed. So you got tons of functions. Now, a lot of these functions are trigonometric. For example, you can notice trigonometric functions, and then you have got hyperbolic functions, exponential and logarithmic functions, and other functions are also there, gamma functions. Why I'm saying these? Power value is an absolute value function. So what is common with these functions is there is a power involved. When I say power, it is of the nature x to the power y. For example, sqrt or cube root or log series. So log series can be expanded to a series. So you got x powers involved. So the first thing which I am going to explain is how to compute x to the power y. Now, x is immaterial here rather. So the important thing is y, because x can be integer or fractional. It hardly matters. But y is critical. Because if y is integral, things are relatively simple. But if y becomes fractional, things are a lot more difficult. But even if we'll cover the fractional part of y later, let's assume for the moment that y is integral in nature. So I want to compute x to the power y. So let's see, I have prepared a simple PDF, one-page PDF. Let me put this in the presentation mode. Okay, so suppose y is integral. So this technique is known as exponentiation by squaring. Just prepared today. This is the basics. This will cover the basic ground for implementing lots of Math.h functions, as you will see in later videos. So suppose I have to compute, as I said, x to the power y, where x and y both belong to I, where I is the set of integers. Now, one of the approaches which you can take is you multiply x y times. You run a for loop and then you multiply x to itself y times and then you store the result. Now, this is all right as long as y is small. You wouldn't have much overhead. And the algorithm is really simple. Sometimes simplicity is of much value, but suppose y is large, say for example 10,000 or so, maybe a million, maybe 10 million. So then you are multiplying 10 million times. That's huge. That's not good. So we need to find something which is faster. So to understand this approach, the critical point you have to understand is any integer can be written as sum of powers of 2. Here I will talk about positive integers, not about negative integers, because even if y is negative, so x to the power minus y can be written as 1 by x to the power y. So suppose I have 1, so that can be written as 2 to the power 0. 2 can be written as 2 to the power 1. And then 3 can be written as 1 plus 2. And 4 is 2 square. And 5 is 1 plus 4. 6 is 2 plus 4. And 7 is 1 plus 2 plus 4. And 8 is 2 to the power 3. And 9 is 1 plus 8. So almost everything, rather not almost, everything, every positive integer can be written as sum of powers of 2. Now suppose you have to compute 2 to the power 25. So how do we compute? We have 2, right? So I write 25 as 16 plus 8 plus 1. So for 1, I have 2, 2 to the power 1, right? So that we have covered. So then we square 2, we get 4. And then we square 4, so we get 2 to the power 4. And then we square that, we get 2 to the power 8. Now see how many multiplications we did. 1 and 2 and 3. So in 3 steps, we get 2 to the power 8. And the 4th step, we get 2 to the power 16. And then we have computed already 2 to the power 8. And 2 is already computed. So how many steps we actually took. So from power 1 to power 4, we have got 4, how many multiplication? 1 to 2, 2 to 4, and 4 to 8, and 8 to 16. So those many steps we have taken for multiplication. That is, we are squaring 2 all the time. 2 is our base, right? And exponent is 25. So in 5-6 steps we compute 25. So this fast you can get your exponentiation done. Now suppose I have like say 1000, right? So instead of multiplying, say 2 to the power 1000 you want to compute. So instead of computing multiplying 2000 times, what you do is you break 1000 into parts. So how do you break? So first part will be 512. So what is remainder? The remainder, what is remaining rather? 488. So second part would be 256. Now what is remaining with 488? That would be 232. Then you subtract 128, you get 104. Then you subtract 96, then you get 8. So those many powers you have to compute. Now to compute 2 to the power 512, what you need to do is you multiply 2 to itself and then that result to itself how many times? 9 times, because 2 to the power 9 is 512. So if you multiply 2 and 2 to itself and the product to itself, then in 9 steps you will have 2 to the power 512. So in 9 steps you would have computed all of them, all the required components, and then one more multiplication with all the computed components, and in the 10 steps you can compute 2 to the power 1000 rather than multiplying 2000 times. So you are speeding up the algorithm roughly 100 times. So that's the basics, and it's very easy to understand. And so this algorithm will be our most fundamental algorithm for computing or generating lots of functions. So here I'll stop this video, and in the next part I'll show you the code for this video, that is how to implement power function for integral exponent, not for the base, integral exponent, and then we will proceed to compute fractional exponents. Thanks for watching the video. I hope you have enjoyed. Sorry for the background noise. I just record the videos. I am focusing on content rather than on the noise. Thanks again.